Okay, so we've done a little bit of work with this already. We're going to do a little round robin reading here. So this is in the appendix. The demand for white Zinfandel in Los Angeles. So let's see, why don't we go whatever seems natural. Yeah, I guess you guys are almost in the core thing, and then let's keep them. So Luke, Eddie, JC, Liz.
Where should I start?
This appendix.
All right.
Oh. Okay. So what time periods were the spikes? Holidays. So Thanksgiving, Christmas, and so you can see pretty flat, 300,000 in unit sales, and then you've got those spike periods, and then figure A2 is down at the bottom. So we got the price of white Zin is this character, Chardonnay, Cabernet Sauvignon, and Merlot. So all of those are kind of tracking with an upward trend, and then we've got the white Zin down there. All right, so that's our data from 1996 through 1999. Comments or questions on the data? All right, next reader.
Scatterplot figure 5A.3 depicts the inverse relation between price and quantity for white Zin. The data cloud is essential for peak observations to the right. As noted in chapter 4, two functional forms are readily available, linear and constant elasticity. Both forms produce reasonable estimates, but fit is better when coefficient interpretation is easier with constant elasticity. The superior fit is not surprising if you consider the CPD function because it is the 4.1a of the previous chapter. For further discussion of CPD estimation, see the non-linearities in cell app CPD motion. This curve fits the data perspective. Figure 5.8.
Okay, so what was the constant elasticity of demand function capturing? We've worked on that a couple different times. Put that in the words and what it's helping address. What did the data look like? Constant elasticity. So JC, number between 5 and 8. 1, 2, 3, 4, 5, 6. Luke.
Yeah.
All right. So let's go back to principles class.
All right.
What's true about the elasticity of demand for a demand curve that is linear? What's true about the elasticity of demand?
Are you asking like if you look at 1% increase in price or something like that? Something like
That would be the interpretation
Okay.
if we did that. But there was some kind of special that was happening to the value of the elasticity along the linear demand curve. So if we were taking points A, B, and C, for instance, what's happening to the elasticity?
Yeah, like the B was like the 0 unit.
Okay, so somewhere along there's the unit elasticity.
Yeah, and you have the A, which is the negative side.
They're all negative.
Or elasticity.
So does it change or is it constant along a linear demand, the elasticity? At points A, B, and C, is it constant? Like, in other words, A, B, and C all have the same elasticity? So we already calculated? No. So that was one of the point. So up here in this range, is this the more elastic range or less elastic range?
Which one? Sorry.
The A range here, somewhere up here. Elastic or inelastic range? Inelastic. So I hear inelastic or elastic? Elastic, elastic, elastic. All right, so our formula is the percentage change in quantity over the percentage change in price. So the quantity changes are really big down here, going from 1 to 2. And so yeah, that was the elastic range of the curve, and this is the inelastic range. So those numbers are less than 1. Somewhere in between here, it turns out to be able to cheat is right there. The elasticity of demand is equal. The point is that it's not constant. So what is this constant elasticity of demand doing? The CED function, the constant elasticity of demand. What is it bringing forth the notion of something that we really didn't do in any of the? It's not linear. What is it? It's a curve, yeah. So there's a functional form that has enough curviness, if you will, that along points A, B, and C, the elasticity is the same. Right? So because of the curviness, if you think about this percentage change in quantity, percentage change in price, it's kind of just offsetting each other enough, right? If we, part of this is the rise of the run, of course. It's really steep here, so we've got a big change in price and a small change in quantity. And then as we get here, it's a smaller change in price and a bigger change in quantity. And so it's just enough so that when you calculate it, it stays constant. So along this curvy functional form with the exponent, that gives you constant elasticity. Okay, so figure 5A3 depicts an inverse relationship between price and quantity. So there's 5A3. Now, is it easy to pick up that there's some curviness to it? Not really, not perfectly. And so that's why you guys with your data too, you might end up doing, depending on what your project is, you might do a little bit of trial and error on what one seems to have the best fit. How do we measure whether something's fitting the data better or not, a certain functional form? What gives us goodness of fit overall for your regression? We run the regression. Yeah, so the t-stats give you what? Goodness of fit for, significance for, not necessarily the data. I want you to be more specific than that. Yeah, the independent variable, the specific coefficient with each one, right? So that is that. So what gives you the overall goodness of fit? If we have B1 x1 plus B2 x2, the R squared, I guess. So now we can kind of use these techniques to see what functional form specification might be better than others. All right, but you can maybe start to see there's some sort of a little bit of curviness, maybe you can almost visualize it. So that's what you'll do at the front end, is kind of do a little maybe trial and error depending on what your situation is. Okay, next reader.
Why fit thought from a full regression was provided in order to emphasize the point described in figure 4.1. The CEV curve in space in figure 4.1a is linear, and log Q and log U space in 4.1b. This linearity allows for estimation using regression analysis. Here the linear regression is.
Okay, so you don't have to read that, but we've already done this work, right? So we transform the data, taking the logs so that the functional form in log form is linear, and we get A plus B1 x1 plus B2 x2, right? So that's all we've done is set up this. R squared 79%, that's pretty good. And then that's the standard error of the coefficient overall. Okay, next reader.
Speak of the dummy variable that equals 1 and then all that each, yeah, otherwise it equals 0. Each coefficient is significantly different from 0. And this regression is more than the 80% of the variance to the right. White set says that will spare the line set plot or regression shown to the
Okay. Yeah, let's go ahead and look. I can't remember. I think the paragraph kind of continues there, but that's okay.
It's just two
That's okay. Let's look at 5A4. There anyway. So remember with the dummy variable, it was like two different regressions, right? It shifted the intercept. So what they're saying is we've got this data over here that seems to fit pretty good, and then we've got this data over here. And when we go back to the cloud, this was the raw data, right? Before the transformation. So that's what it's picking up is these little guys over here is the bump up in quantity because of the season. So those dummy variables are significant, which then gives you those two different line plots. Okay, so we'll continue on. Let's take a peek here. So you guys will have some sort of table resembling this in your paper when you display your results, right? We've kind of seen that in other ones too. So here, the way they've got it designed, a lot of times the variables will be along this side, so it could be flipped around in different pages. You'll see it presented differently. The way the author did this, A through H, and you can see the variables that were included and excluded with each run, right? So when we take all of the variables, what problem do we run into when we throw in Cab, Merlot, Chardonnay on the price? What did we call that problem where we might run into when the variables tend to move together? I'll give you a hint. It's when the variables are collinear with each other. Nope. Multi-collinearity. So if we look at this one, the T statistics and stuff start to get a little wonky on us potentially, switching around different signs. So when we think about wine, going into the study, what would you expect them to be? Complements or substitutes? Two different wines, white Zin versus Cabernet. Substitutes, right? So one goes up, the price of Cabernet goes up, people buy more or less of white Zin if they're substitutes. Price of Cabernet goes up, more. We buy less. More level. So the two are substitutes. Let's say that's our hypothesis test, right? Now we're going to go to the data. Maybe they'll turn out to be complements, but let's say we go into it thinking that they're substitutes. So when we set up the hypothesis test, if Cabernet gets crazy expensive, what's going to happen to the quantity of white Zin? Increase or decrease? Nice and loud. I say increase. If Cabernet goes down and gets cheaper, decrease. So what is the sign of the cross-price elasticity that we expect going into the study? Positive. They move together, right? So when two goods are substitutes, then we expect there to be a positive sign. Just the opposite true with complements. If one gets more expensive, we buy less of the other thing. All right, so here's our coefficients. When we run white Zin on its own with A, do we have a significant coefficient on its own price? So PWZ is the price of white Zin. So is that a good statistic? Is it significant? Yes. Yes. Why? 5.21 is greater than 2. So then we're using our rule of 2. So that's fine. When we add Chardonnay, so now we've got Chardonnay and it, does it remain significant?
Yes.
Yes. What's happening to the magnitude of the coefficient? Is it getting larger or smaller? So we talked about significance and we talked about size or magnitude. It's getting larger, right? So 2.36 versus 1.82.
Is that just because it's absolute value? It's not.
So we want. So let's go back, Luke, to your interpretation. Interpret. Let's start with the first one. Interpret that one in Model A. You were starting to do it before. Interpret this. This is an elasticity, remember, because we're doing the natural log.
So that's also your price of the white Zinfandel, right? So if you if you change your price 1%,
okay, good.
You have a 1.82% change in your demand.
Increase or decrease?
Well, if you have a 1% price increase, you have a 1.82% decrease.
Good. Right. Okay. Now interpret this one.
Same thing. You have a 1% price increase. You have a 2.3% price.
So which one's having a bigger effect or a bigger magnitude?
The second.
The second. Right. So we're getting a 2.3% bump or change or response by consumers. In this one, here we're getting a 1.82% change. So there's kind of a bigger effect, right? The magnitude is bigger. So that's how you report this in your final papers. When you guys are interpreting stuff like this, you'll say that the effect was bigger, or there's the interpretation, or whatever your context is for your paper. You're going to have something along those lines. Okay. So then Model C, what's going on with Model C, the way you look at this compared to Model B? C compared to B. What has the author done, or what has the researcher done with C as opposed to B? Good. So we're just independently testing cab instead of Chardonnay, right? So that's where you see these blanks. It depends on what variable they're running. So when they run their regression, they're just running cab only without the Chardonnay. And is it significant? No, 1.17. So right here, we were at that minimum threshold with Chardonnay. Then we run this one independently. Then we jump down and we run both of these two. And now we might start to be running into the multicollinearity problem. Look at what happens to the sign. It's switched. So remember when we went through that exercise, if it starts going flippity-floppity on you, that's probably a multicollinearity problem, which means it's probably not appropriate to run both of those terms. And then we've got F, and then we got G. We're just running all these pairwise comparisons, and then we run the whole kitchen sink. All right, so that's kind of a quick snapshot of the data. We've got the R squared, adjusted R squared here, where we adjust for the number of variables. Still remaining pretty strong across the board. Okay, back to the reading.
I got a question.
Yeah.
So on that very last one on page, so we have the Chardonnay as a complementary group, and then we have the other two as substitutes. So am I reading that right?
Because you're looking at the sign, I assume, right?
Yes.
Okay, but what else is true besides the sign?
The value, actual value.
Yeah. So the value and are they significant?
Yeah, so the second two aren't significant, so would be included.
Yeah. So they'd just be treated as zero, that they're insignificant.
Okay. And then you have 2.29, so that be the complement.
Yeah. So now is it complement or substitute when it's a positive sign? Price of Chardonnay goes up, quantity of Zin goes up because it's positive. So those are substitutes. Okay, so who's the next reader? Let's see, where did we leave off exactly? Yeah, right here.
Ranging from -1.82 to -2.3.
Okay, let's just pause there for a second. Go back and look at the table. So here was the time counter. So in this, we had a significant coefficient on the time, but it's still fairly small. So that's what they mean by it being flat. And then it kind of varies depending on which one we go to, whether it was significant or not. So this part of this is kind of handy. This is the type of way that you describe it for your guys' paper describing the data. So you'd have written out some stuff like this. So this is what the economists would call a robustness check. Like, how robust, how strong is your estimates? We throw different variables at it, and the elasticity here seems to stay in that, kind of that similar range that they specify, right? And so the 2.35, the 2, so they're all like, no matter what we do running the data, it seems to stay in that range. So we're pretty comfortable that it's passing a robustness check. It's a fairly robust number that we can be pretty confident that it is elastic, at least in the elastic range. And furthermore, in that 2 to the 1.82 to 2.36 range, right? You see how we're kind of testing that, and it's like, oh wow, that seems pretty resilient to different model specifications, and so we can start to be more confident about that. Yeah, F. Okay, any other questions or comments there?
So if your thing is not between a clause and negative one, then it's elastic.
Right, that was this. If it's less than 1 or equal to 1, but we're pretty significantly above. 1.82 is the low end, and 2.36 is the high end. So we're pretty confident we've got a decent elasticity.
And how do you calculate elasticity again in the regression? How do you get that? Like where does 1.82 come from?
With that specification, you're taking the logs, so it ends up being the coefficient with the constant elasticity demand formula. So when you take your raw data and you transform it with the log transformation, the coefficient ends up being the elasticity.
Can you do that with stock prices?
Yeah, I mean, if it fits the data, so when you use the constant elasticity of data, you have to be a little bit mindful of what does the original data look like. If the original data is, definitely a straight line or something, then you wouldn't do the log transformation. Okay, next reader again. So model F. And remember, we have the rule of 2, but that is a rule of thumb. So with this number of variables, 1.89 turns out to be significant if you go back. So the rule of the 2 thing is just, so if you get one that's close, then you really need to go look in that table to see if it's significant or not, depending on the degrees of freedom that you have. So it turned out 1.89 is significant at the 5% level. We have the highest R squared, adjusted R squared out of them. So we got 2 significant variables. We got one being positive, one being the substitute. Merlot is a red wine. This is another white wine. So Chardonnay and white Zin both being whites, right? So that's kind of the picture that the data is painting in terms of the interpretation. Okay, questions or comments there? All right, continue on. So now the next part of this gets into kind of what your exercise is going to do. You're going to go through and replicate what they've done. So using Excel to perform regression analysis, a number of available statistical softwares such as SPSS and SAS can be used to perform regression. In this section, we demonstrate how the most readily available generic software package, Excel, can also be used, which of course we've been using. The data used to perform the analysis is located in data with seasonality. 5 columns of data are in there, 5 lines, all the tables. When performing regression analysis, it is convenient to create a separate worksheet that contains the regression data. This worksheet is called data reg. In this section of the appendix, bold-faced letters refer to Excel names, numbers, et cetera, So the rest of what this thing does is it walks you through, and we'll do a little bit more of this, kind of hold your hand all the way on stuff that you did, like some of the stuff you guys can breeze through. They're going to do the chart, the lines, telling you exactly what to do to recreate what was done. And so that is this whole appendix to regenerate all the way over to 174, just to kind of foreshadow it.
That's what it's all about. Right?
Yeah, so go ahead and pull up Excel app 15, not 18. Or does it say 18 somewhere? No, 15. Okay. So here it is. So mine opened up to data reg, which is what he said with the new tab. Here's the raw data. So if you click on the left tab, just to kind of look at the raw data, this might be what you guys will get as your data hunting. And so you get columns across the top, white Zinfandel sales, sales volume for white Zin, unit sales. So there's a whole bunch of different data that came across. So this is the raw data, which sometimes will need to be transformed. So then if you go to data reg, he's got the transformation started. So we're taking the log of L2, so he pulled over the data points that we wanted. So if you double click this A2 cell, oops. So we've got the unit sales taking the log of it. So same thing we've done with the other exercises, right? So you took the raw data and put data reg so that we don't have to look at all that other old data, right? And it's good to have a fresh sheet that you're starting with. Remember when we run Excel that your independent variables need to be contiguous with each other, the columns do, so that you can just easily drag all of them when you do different runs. So this is all just part of the data manipulation. We've got the raw prices, and then we end up transforming into the logs. And then we can start generating the output. So basically your goal here is to generate the output. You can think of this being like the answer key, but you guys should run it yourself. So you're kind of pretending like you're the researcher doing what they've already done. And they've got the peak lines, all these little check boxes. All of that is back on this sheet. So if you want to try doing this analysis yourself, which is what you're to be doing, open your own blank document by clicking the new blank document on the standard tools, file ribbon. So some of the stuff you guys have already done, like started your, copy the entire data worksheet to the new workbook by opening a new file and then going back to it. Highlight.
Right, you can open a new tab next to the.
Yeah. Yep. So just kind of start fresh, because when you have a blank slate that you're looking at, it's a little bit different, and that's the blank slate that you guys are going to be looking at with your analysis. All of a sudden, you're going to have this data, and then what do I do from there? So here, this section here is just telling you to move and manipulate the data. So now create the data reg sheet. So you're starting from that raw data and start to recreate that. Figures are easy to create using the chart wizard, standard tool. Then you can create some of those charts that they did. So it's good to look back at the data reg. So you guys might have some of this in your paper. So that was recreating what we saw in the textbook already. So just how do I do that? And then they're going to show you how to plot that data and make these pictures. Okay. So that tells you about, that tells you about the figures. And then it runs you through all the regressions. So I'm gonna leave the rest of the time. You guys start working this out and talk amongst yourselves and get into it.